this one over here, I will take this term and manipulate this a little bit. So this minus mr theta dot square, by using the expression from the angular momentum for theta dot, I substitute this in here. I get minus L squared by r cubes. Okay, so L, just the expression for L goes in there. And I can take this and write this as a partial derivative of r. And so this is going to be a half partial with respect to r of L squared by r squared. So I can take this and put it in here, and then take this whole thing into a total partial derivative. So my potential is going to be, or let's define a pseudo potential. This is just my potential plus L squared by 2m r squared. This expression over here. Okay. So it is as if that my force, for the radial motion, my force is mr double dot, and then on the right hand side, I have some effective potential, some pseudo potential, where the partial derivative gives this mass times acceleration. Okay? So this thing over here is called the centrifugal barrier. Okay? So that's what's responsible for you not falling into sun directly. Okay? So the sun is of course attracting us, right? But we are not falling into sun. Why are we not falling into sun? Because we have angular momentum, and that angular momentum leads to a modification of the potential we feel. The potential we feel is not just 1 over r, is not just this 1 over r potential, but there is a centrifugal barrier which prevents you from approaching the sun arbitrarily. And again, this is not something that happens in general, that this force could overcome the centrifugal barrier, but for the Kepler potential, it does not. And so let's look at this particular situation and see if we can say something about the orbit by looking at this. And so I'm going to say, just for this one, let's see, let's keep the signs correct. Are they defining this as 1 over r or r? Let's see it. Anyway, I'm just going to say r is minus 1 over r. So what does this look like? It looks like this. This one. This is your r. Now this one is positive. It's 1 over r squared. So we're going to have something like this. That. Okay. This is 1 over r squared. And there's going to be some competition between these two. Right? When r is very large, so this v of r, this v of r is the 1 over r potential. When r is very large, 1 over r squared dies off better than 1 over r. So this is going to win. At large distances, this is going to look like our normal potential. At small distances, when r is very small, 1 over r squared gets larger much faster than 1 over r. So this is going to win. Right? So near the origin, this is going to behave like this one. Right? Near far, it's going to behave like this one. And in between, we're going to have this transition. Okay? This is going to go through some minimum and go from the 1 over r behavior, negative 1 over r behavior, to a positive 1 over r squared behavior. This is the potential that we are going to get. So this is what our what I call V tilde looks like. Okay. All right, so by looking at this, we can tell now what the behavior of the motion in r direction is going to be. Now, let's say that our energy, and just start with something simple, our energy is over here. All right, let's call this maybe E1. Now, what kind of motion will this lead to? So, have you seen the analysis of motion by using this potential diagrams. This is something we sometimes do in freshman physics, but it's also probably done in the undergraduate classical mechanics. Wow. So the analysis goes as, you have some at this point, this is the potential, it's going to lead to a force in this direction, so you're going to go this way, and then when you come over here, the force is going to reverse, and so forth. And you are not allowed to, go to a point where your energy does not permit you. So here, I cannot go beyond this point. Okay? So this is going to be my R min. Beyond that point, the potential is going to be so negative that I can't actually, I can't go beyond this R1. My total energy will be negative if that was the case. Okay? I run out of kinetic energy. Here, I have pure potential energy. I come to a stop. This is my turning point. All the energy is potential energy at this point. So I turn and then move in this way. But there's nothing stopping me in that direction. Right? I go indefinitely in that direction. So if I'm coming from infinity, I make a turning point at R min, and I just escape to infinity again. This is what it's going to look like. This is an unbound system. I have too much energy. The system is not going to be bound. Remember, this is relative motion of two masses. Okay, so that's why I'm referring to when I say unbound, those two masses are not bound to each other. Now, I could have another energy over here. Okay. And this one has two turning points. Let's call these R1 or R1, R2. Yeah. So what's going to happen here is that, let's say you start this way and you're going to the left to smaller and smaller R. You reach this R1, you have to stop there. All your energy is turned into potential energy. You have no kinetic energy. You stop this momentarily and then you turn around, you come over here, you pass through the minimum of your potential energy, which is the maximum of your kinetic energy. And then you come over here again, you run out of kinetic energy. All your energy is potential energy. This is another turning point. You just go back and forth. So you're going to have two turning points in your orbit in the radial motion. And one of them is typically called the pericenter distance. The other one is going to be the apocenter distance. Okay? For the minimum R and maximum R. This is not saying anything about the theta motion. So in general, that motion is going to look like this. So all these outer points are my R2. I always come to a turning point there. And all these inner points that I'm turning around again is my R1. That's the kind of motion that you get. Now, we know for this potential, this is not the motion you get a closed ellipse. But just by looking at this, you cannot tell. Okay? This analysis only tells you that there's going to be a minimum R and there's going to be a maximum R. This cannot tell you whether the orbit is closed or not. The fact that the orbit is closed comes from some lucky cancellation. But we can do one more thing. We can say that our energy is going to be here. Yeah? Just at the tip point over there. That would correspond to a circular orbit. Your R is constant. You cannot go anywhere. Right? You're just stuck at this point. And there is no force. The nr double dot in that case, the right-hand side of this is going to cancel completely. Right, the sum of these two, its partial derivative is 0, means that this mr double dot is 0. So there's no radial acceleration, and you're just going to sit there at the given point. And that corresponds to a circular orbit, something very simple. And you can, of course, take this, write the effective potential for a given force potential and see what that energy corresponds to. Right, you take the partial derivative to 0 and you substitute back in. All right, now this does not need to happen. Okay, so we said that this 1 over r squared is going to overcome this minus 1 over r near the center. Well, for another force, this is not going to happen, right? If this was the force, if the force was 1 over r cubed, for example, then the potential will be minus 1 over r cubed, something like that. And this will dominate both near the origin and there. You will perhaps get some local minima and maxima, so you can get some interesting orbits. Again, it depends on the coefficients. That much you cannot tell by the asymptotic analysis. but this whole picture will completely break down. Right? So this is somewhat a property of this kind of motion. And of course, you could have 1 over r plus something, 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 and then 1 over r could dominate at large. This is not something that should always happen. This one doesn't change. The centrifugal barrier is always a 1 over r squared force. It's always something like this, some addition. And I think the reason why this is called centrifugal barrier is kind of obvious. This looks like a centrifugal force. And if you take derivative of this, it looks like the centrifugal force, which is the force that you would observe in the non-inertial frame. Right? In the inertial frame, it will be the centripetal force that leads to the whatever motion you're experiencing, the relative motion. In this case, the elliptical motion of the two bodies around their common center of mass. Okay, so this is one way to classify the orbits. It works for a specific class of potentials, but yeah, this is it's so important, this particular class, that you of course have to mention this. The other important class is this one. Here are. So this is something you can, that we encounter all the time. And can we make an analysis like this? Right. So the potential is now going to be an r squared potential, not 1 over r potential. And can we actually do some analysis? The answer here is you don't need to. This just by looking at this, you can write the two components. Let's say that this is again a central force, so it's going to take place in a plane. I'm going to just use Cartesian coordinates for the plane. This just decomposes into this. And the solution to these are just harmonic functions, provided that this is in fact the normal spring. This is going to be sines and cosines, and we already know what the two sines and cosines do. Right? If they have the same amplitude and if they have a proper phase difference, then you're going to get a circle. Otherwise, you get an ellipse. This is what's going to happen in this case. You don't need to do an analysis like this to classify the orbits in this case. And for everything else, yeah, it's either looks like this, or you have to know the coefficients to make a more detailed calculation. And I'm not going to go into this. And I'm not going to go into when you get the closed orbits and things like that, Bernard's theorem. I think it's fascinating. It's nice, and for a mathematical physicist, I'm sure that there's some stuff to study there, but we're not going to use it. If we actually get to use it, then yeah, we can just use the results. There's one thing that again might seem like a side topic over here, but it is so central to a lot of things in classical mechanics and celestial mechanics, and it also spills over to statistical mechanics, that I want to spend some time on it, and that's virial theorem. So this can be expressed in a number of ways. It is somewhat like Noether's theorem. So Noether's theorem, you can express in a lot of levels. Like you can express Noether's theorem to a high school student. But you can also express it in graduate classical mechanics class, which I hope you'll get to do this course. And they look completely different, but they actually are talking about the same thing. The virial theorem is also a little bit like this. There are different expressions, but it comes up again and again. So I'm going to spend a little bit of time. Now, first of all, this theorem deals with average quantities. Okay, this is something we don't normally do in classical mechanics. This is something we do in statistical mechanics. And in fact, the origins of this is in statistical mechanics as well. But whenever you do something like this, you have to define how you get the average. So how do you get the average in this case? In this case, it's simple. But in statistical mechanics, sometimes it gets really complicated. Like, are you taking the ensemble average? Are you taking the particle average? Are you taking the space average? Are you taking the time average? All of those are average. In this case, it's defined with time average. And I'm going to define the time average this way. So if I'm taking something, so the book is using a bar or quantities. I think the vectors and everything is just going to be too messy. So I will do it differently. So it's going to be 1 over tau. Tau, whatever this quantity, dt. Okay. So without doing this, you have the risk of running into trouble. Right? Okay, so we first define, we first restrict ourselves to a particular system. So you could say that we just have some constraint forces and we're in Cartesian coordinates, something like that. Yeah. Just good old fashioned, nothing funny is happening. This is what this is saying. Now we also define a quantity, which looks funny at first, but it's going to turn out to be useful. And we sum over the averages here. The I, as usual, stands for the sum over the particles here. I'm sorry. It stands for particles. So we define this and consider the partial of this quantity with respect to time, or not the partial, total derivatives. Okay. Now this is a dot product, so we can just apply the derivative rule for the dot product. So dg by dt is going to be two sums, pi dot into ri plus pi dotted into ri dot. Okay. Now this one, what's this? Well, this is mv, this is v, this is twice the kinetic energy. Okay. So we didn't go into funny coordinates. So this is just going to be our kinetic energy. This one, the first term, there's a dot on the momentum here. So this is just fi. It is just the sum of fi dot ri. Okay. Now I'll take the time average of both of these quantities. I need some space. I'll just erase this. 1 over tau dg by dt times dt from 0 to tau. Now, this is a total derivative, so this is just going to be 1 over tau g tau minus g 0. All right, so and this is going to be the time average of 2t plus the time average of this f dotted into ri. Now I claim that this integral is 0. Okay, so I'm taking the time average, this quantity, and this is 0. Or I can choose my tau to make this 0. Now how? Well, if the system is periodic, then I can choose my tau to be some multiple of the period, and then this is identically 0, right? Has to be. Because if it's periodic, then it repeats itself every tau and every period, and if tau is a multiple of the period, then it just becomes 0. Now, if it's not periodic, then I can make this tau very long, And as long as this position and the velocities are bound, they have to cancel out. That I can find at some point that these quantities are going to cancel out. Now, there's a maximum in engineering that there are only three things a system can do. Okay? Take a system, it either explodes, it just dies out, wimps out, or it oscillates. But this is really how all the physical systems work. Of course, if you could be looking at this for a very short time scale, and it could be in a transient state that you can't tell whether it's going to oscillate or die or explode or something like that. But this is what. So if the system is exploding, if the things are becoming unbound, and unphysical, okay, our position and momenta for arbitrarily large tau is going to be finite. So we're not looking at that. And if they are dying out, then I just make it so long that the died out parts dominate, and this is just zero everywhere. So of course, this difference is also going to be zero. And if it is oscillatory, then it either is periodic, it's repeating itself, or it's chaotic, and it's not repeating itself, but in some sense, it is random. So over long time scales, the time average is just going to cancel out, or it will become arbitrarily small to make it more formal. I'm not going to prove this, but this is in fact can be proven. So I'll just state that this can be made zero by choosing your tau appropriately, either by making it alone, by some multiple period, by choosing something nice. But you need to keep in mind that this doesn't happen for arbitrary tau. Right. And then we get this. Okay? So the time average of these two quantities is the sum of the time average of these quantities is zero. So the time average for the kinetic energy is going to be minus a half this little sum time average. And I can write this as some gradient of the potential dotted into these positions. Okay. So this is the no, this should be the I sign. So this is the gradient of the potential with respect to some coordinate dotted into the position associated with that coordinate. Okay. All right, so again, we can go only this far without specifying what our potential is. For our single particle central force problem, this is just k over km over r, something like that. So let's substitute that. We now go to a single particle central force. Okay, so our time average of the kinetic energy is going to be a half LV by the R times R. Okay. Our potential only depends on R, so it has just one component. The gradient has just one component. The component is R, and so this just becomes a normal product. It's normal gradient. Now, if of R is A R to m plus 1, that is to say, f of R is proportional to R to the n, then your time average of the kinetic energy is going to be m plus 1 over 2 time average of potential energy. And for n equals minus 2, which corresponds to central square force problem, we get time average of T is minus a half time average of V. Yeah. A result perhaps you're already familiar with. This is typically mentioned in four-atom model, in modern physics, and perhaps in quantum mechanics as well. All right. So this has other applications. Like we use virial theorem in other forms in cosmology. For example, when you look at when we try to estimate the mass bound in a galaxy cluster, this comes very handy because what you can measure is velocities, and from that you want to go to the total potential energy, and the same relationship holds because basically it's gravity, right? It's a 1/r potential. But this is another interesting consequence. So the time average of kinetic energy is minus time average of potential energy. So if you look at the total energy, and this is of course the sum of these two, and one way to write this out directly here. So T minus 2T. And this is just minus. Your total energy in a bound system is going to be negative, so this is not very surprising. But there is something very strange here. So if you have a system that's just bound by gravity, so 1/r force, so this relationship holds. The time average of your total energy is like that. What would happen if you inject energy into the system? Or if you take away energy from the system? So normally, right, if you have this room around me, you have a room full of gas. If you inject energy into the system, the kinetic energy of the gas increases. Right? This in an ideal gas, this is what happens. But ideal gas has this interesting assumption that the particles do not interact with each other. Here we have kind of the opposite situation. The particles are bound by each other. They're heavily interacted. They're not bound by some container, but this is like a star cluster that's just bound by its own gravity, a self-gravitating cluster. And a self-gravitating cluster is going to have this relationship. This will also work for just two masses, right? Maybe it's simpler to think of two masses, but it's more fascinating when it's a cluster. What will happen if you inject energy into the system? Or more dramatic, what will happen if you take away energy from the system?
If we inject energy to the system, would it become unbound? For example, if it goes
not that much energy. If you have energy, the cluster tears itself apart, of course, but you don't want to do that. So maybe it's better to think if you take away energy. It's already bound.
So if we take if we are thinking about like minimum I don't know, kind of differential, small type of energy, then should it oscillate?
No.
I'm assuming no.
That's not what I'm looking for. It could perhaps, it could do something depending on the interaction, how you put the energy, and so on and so forth. But what will happen is that this total energy is going to go down, which is already negative, and that will lead to an increase in the kinetic energy. So if you take away energy from the system, the kinetic energy is going to increase. The particles are going to move faster. Now, the motion of the particles is associated with temperature. So when you take away energy from the system, the temperature is increasing. This has negative heat capacity. A gravitational bound system, because of this virial theorem result, has negative heat capacity. And this is something we actually see. This leads to the so-called gravithermal catastrophe in star clusters, that the central parts, they are more bound, so they move faster. And because they move faster, their temperature is higher. As they interact with the outer parts, they give away energy. But as they give away the energy, their temperature increases. Their velocity increases. As their velocity increases, they have more tendency to give away energy, and eventually they become very tightly bound. We have the core collapse. Or the core collapse is stopped by the collapse of the binary stars and so on and so forth. But this is something we can actually see, and it follows from the virial theorem. You also have, as I said, applications of this in cosmology when you look at the galaxy clusters. And the best way we know to estimate the mass of a galaxy cluster is by measuring the velocities and applying the virial theorem. After we apply the virial theorem, well, not exactly in this form, but you can get a sense of the mass of the cluster. Okay. Now, there is also a discussion of this, how it applies to ideal gases in the book. I kind of skipped it, but it is, if you're like in statistical mechanics, you see this result, how this ideal gas law is driven and so on and so forth. Just take a look at this. Okay? And if you understand this argument, then you're going to understand how it applies to statistical mechanics. Perhaps it's going to answer some problems. Now I want to switch to the elephant in the room. We are now going to talk about the Kepler problem. Okay. So we have made the general arguments as far as we can do. We are going to stop beating around the bush, so to say, and look at 1/r potential. So Kepler problem is sometimes used for just the electrical system, and here they're using it just for the inverse square level force. So our F is going to be given by some k/r². Our potential is going to be a minus k/r potential. So this means our energy is going to be half v² minus k/r. Now, so there are some manipulations that are there in the book, and you start with this, and then you get this very funny looking result. I'm going to write this down because I want to make some identifications using this, but I'm not going to do the manipulations given in the book. It's a little bit, it's not very modern, let's put it this way. Theta prime. Okay. And you can, of course, absorb all of this into some constant. You can write this as c 1 plus e cosine theta minus theta prime. Okay, so this is what's given in the book. This e is called the eccentricity. This is the equation for a conic section. Right? So it turns out that this kind of force or this kind of potential, they're equal to each other, leads to orbits that are conic sections. Right? The fact that this is a conic section was known for a very long time. This is not something that we need to prove. This is also sometimes written as r equals p over 1 plus e cosine theta minus omega. Okay. So this symbol here, omega. This is a archaic way of writing Greek letter pi, but it looks like an omega, so we call this omega. And there's of course no letter called omega in the Greek alphabet, but that's we're going to refer to this. Okay. And this one would be called the similar spectrum of the conic section. Now, how would you drive this by using? So I want to drive this equation, okay? And you can check the book if you like that sort of thing. Those manipulations that they do in the book, knock yourself out. But I think there's an easier way to get this than what is given in the book. And I'm going to start by substituting this force law into my equation of motion for radial motion. So mr double dot minus mr theta dot, no, this is, yeah, equals minus k over r squared. This was the equation of motion. So r double dot minus r theta dot square is minus k over m over r squared. Okay. I try to make things dimensionless, and I write it this way. Now I'm going to take this equation and apply two tricks, and I'm going to turn this into something that I already know the solution to. Right? This is what I plan to do. So the first trick is the substitution. U is 1 over r. This might look like, okay, you kind of knew the answer, so you're making the substitution. This is cheating, but this is a very common substitution in system mechanics. This is one of the first things you will try if you're trying to solve an equation like this. And the second one is that I'm going to use the fact that r squared theta dot, which is L over m, is a constant. So if you take this and put it in there, let me erase this. See it perhaps. So if you make that substitution, so we are assuming r is a function of theta. Okay, so we are trying to get the r that we are dealing with here is a function of theta. We are trying to get the equation for the orbit, not the equation of motion. So we are not considering r as a function of time. We'll just get a relationship between r and theta. So it does depend on time. R, of course, depends on that, but only through theta. The r we are dealing with here is a function of theta. Okay, so keep this in mind. And with that in mind, actually, so dr by dt is going to be minus 1 over u squared, oops, du by dt, and this is going to be minus 1 over u squared du by d theta by dt. Just a change. Okay. U, just like r, is a function of theta and depends on t only through this relationship. And this I can write by using this angular momentum expression as minus L over m du by d theta. Now I can take the second derivative, d squared r by dt squared, and this is going to be minus L over m, just writing the expression over here, e by d theta of du by d theta, and just like take a dot. Yeah, this way. And just like the first case, this is t. I have a stick in my notes. Sorry. Yeah. I'm going to take the with respect to theta and introduce theta dot. So this one, after some manipulation, is going to give you minus u squared L over m squared d squared u by d theta squared. Okay. I'm skipping some steps, but they're not very hard to do. Okay. So I take this and put this over here. I take this and that's it. I an expression for that over there. I have to erase something. I can't make these fit, unfortunately. And we get in the end minus u squared L over m squared d squared u by the theta squared minus 1 over u to the 4th L over m squared. This one comes from substituting this into that. Okay. Equals minus u squared k over m. Okay, and we can rewrite this as e squared u by the theta squared plus u equals k over m by h squared. And h is okay. So what's the solution to this equation? D squared u by d theta squared plus u is k over m by h squared. So we took our Kepler equation and turned this into this one. Eventually, I want to go back to r. Of course, I want to express r, but this can be solved for you. You know this differential equation. What is this differential equation? Are you ready? Can you recognize this?
Exponential decay
Uh,
in theta.
the minus sign it would be.
Ah, yes.
This is plus.
Okay, so it's an oscillation.
Is it oscillation? If the zero, this would be harmonic oscillator.
Mhm.
But it's not zero.
It's a particular part.
Yes.
Mm.
So this is an inhomogeneous. You need to find a particular solution
Mhm,
and combine with the solution to the homogeneous equation and get the general equation, right?
mhm.
But physically, what does this correspond to? So, like a square x by e square plus x is, oh, have you seen anything like this? Like with zero, it is harmonic oscillator, right? You have something on a spring. But if there's an external force, and that external force is constant. Did you ever encounter a situation like this?
Is it like the dumping force?
No. Damping force will depend on velocity. It won't be
Yeah.
constant. This is a constant force. What does the constant force do?
Forces the system to go further, like it's a forcing force.
No. So if it's a driving force, it will be time-dependent force. The driving force for harmonic oscillator, it's not. It's constant. But you have seen this before. I guarantee you have seen this before. It's a spring in a gravitational field. Right? So you have a spring, but it's not on a table, but it's in a gravitational field. So what does this do? It shifts the equilibrium point. It shifts it to the point where the restoring force on the spring cancels the gravitational pull. Right? And then it's not going to oscillate about its original equilibrium point, but around this new equilibrium point. But it will still do some harmonic motion. And in this case, the spring constant is 1. So the shift is going to be, this F external divided by the spring constant. So the shift is going to be just this much. Right? And that's what you get. So you get a cosine, not theta, but something shifted. Oh, sorry, this is just general. There's a shift. There's going to be some shift over here. Some, yeah, let's call this shift. Sorry, I misspoke. So this one is the phase shift. That's always there. This one is coming from the presence of the external force, this term over here. And because the force constant, the spring constant here is 1, the shift is going to be equal to the external force itself. Otherwise, to the external force divided by spring constant.
Now,
And it is.
Sorry.
Go ahead.
Is the phase shift related to the particular parts or just
No,
the?
it is related to where you start. Right.
The
So
homogeneous
that's
part.
determined by the initial conditions.
Okay. Thank you.
That's not really part of the solution, but you have to put it there. Okay, so it is this equation, and that one is going to have a solution of u equals k over m by h squared, which is mk over l squared, of course, but 1 plus e cosine theta minus negative. So I have two constants of integration. One is here, the other one is here. Right, this one is the amplitude of the oscillations. Well, this times this is the amplitude of the oscillations. That's determined by how much energy you put into the system, and this one depends on when you start it. This one is not a constant of integration. It comes from the fact that there is a additional force, a constant force in your system. Okay, so you don't need to go through all that analysis in the book. I think this is a little bit simpler, and it's not something that you would consider cheating if it's something you do test mechanics all the time. Now, as I said, this is the equation for a conic section, and there are some classifications for this. So this eccentricity, E is eccentricity. And it is equal to some 1 plus 2e L squared by m k squared to a half. I might be making mistakes here. No, I don't check these very rigorously. In fact, I might have just copied this one. The form is not very important. The data is not very important. Important thing is the form. So this is 1 plus something proportional to E. Okay? So depending on the sign of E, this is going to be larger than 1, smaller than 1, or equal to 1. So let's look at those cases. If E is larger than 0, then your eccentricity is going to be larger than 1. Okay? And this is, what does this correspond? This is a hyperbola. In this case, so I erased this, but I had introduced similar to stratum. The similar to stratum is a particularly simple form. So if E is equal to 0, then your eccentricity is equal to 1. This is a parabola. And if E is less than 0, then if the energy is less than 0, then E is less than 1. This is an ellipse. And this is by far the most interesting one, of course. And there's a particular value of E minus K squared by L squared. But there must be 2 somewhere, 2L squared. Okay. This corresponds to E equals 0. That's a circle, a particular case of ellipse. Obviously, you can't make E a number because I'm taking the square root. This whole thing cannot be less than 1, and the eccentricity is going to be imaginary. You don't get a conic section in that case. Right? So, and the reason why we call these conic sections is because these are the curves that you get when you have a cone. And when you intersect this cone, the plane, depending on how the plane is oriented with respect to the cone, you get one of these curves. If it's perpendicular to the axis of the cone, you get a circle. If it's intersecting, so let's say that there's another ellipse over here, intersecting only one of the ellipses, you get the one of the cones, you get an ellipse. If you're intersecting it vertically, you get a parabola. If it's in such a way that it's intersecting both of these cones, then you get hyperbolas on 2 sides. And hyperbola has, of course, 2 branches. Right? So this is why this is called conic sections.